So I would like us to write out a few terms of this formula for arctangent x to get some feeling for how power series represent functions. So this series on the right starts off like so. We have arctangent x is equal to, when k is 0, we have 1, and here x divided by 1, so x, then minus 1 to the 1 gives us minus 1, and for k equals 1 we have 3 here, x to the third divided by 3. Then this sign switches again, and we have plus x to the fifth divided by 5, and so on. So the important observation to make here is that arctangent is an odd function, right? Meaning it is symmetric with respect to the origin. F of minus x is equal to minus f of x. And on the right hand side, we have odd powers of x. So this right hand side is also an odd function. So this property will be true in general. Whenever you obtain power series expansion for an odd function, it is only going to contain odd powers of x. Let us do the same now for the power series representation of log of 1 plus x. So we have shown that log of 1 plus x is the sum k from 1 to infinity minus 1 to the k plus 1, x to the k divided by k, and this expansion also holds when absolute value of x is less than 1. Note that the indexing starts at k equals 1 here, not at k equals 0. So this series starts off as follows. We have log of 1 plus x equal to, for k equals 1, I have minus 1 to the second powers, which is equal to 1, and then x to the first divided by 1, in other words, simply x. When k is equal to 2, I have minus 1 to the third, that is equal to minus 1, and this here is x to the second divided by 2. Then the sign switches again, and I will have x to the third divided by 3, and so on. So as you can see, now our function is not odd. Log of 1 plus x is not an odd function. It is not symmetric with respect to the origin. And so, accordingly, in the right-hand side, we have both odd and even powers of x, which is in line with what we said about the previous function.